In this video, I will demonstrate how you can use the classification tree that we built in the previous video for predictive purposes. Notice that the tree that we are going to discuss in this video is built using the tree package of the R statistical programming language version 3.3.2, and the tree is first overgrown and then pruned to a size determined by a tenfold cross-validation performed on a training set. These are important technical details behind the tree building process, which nevertheless are beyond the scope of this video. Now let's learn how to interpret the classification tree. Suppose we have a patent application that we're trying to classify, and at the root node, the following question is being asked. Is the number of prior efforts made at patenting the application less than 2? Now, if the answer to this question is affirmative, in other words, if the number of prior efforts made patenting is either 0 or 1, then we're moving to the left branch of the tree, and we see right away that we arrive at a terminal node where the label appears to be pending. In other words, for all those patent applications that either have no prior efforts or that just had one prior effort, according to our tree, they're classified as pending. On the other hand, if at the root node the answer is not affirmative, then we are dealing with patent applications that have 2 or higher prior efforts. If that's the case, the next question that is being asked by the tree is whether the prior efforts are fewer than 6. If we answer that question affirmatively, then we know that for those patent applications, the number of prior efforts is anywhere between 2 and 5. Then their fate, it turns out, will depend on their claim volume, as that's the next question that's being asked. Is the claim volume of those documents less than 24? If, in fact, the claim volume is less than 24, their fate will then be determined by whether or not their claim volume is, in addition, also less than 17. And if we answer that question affirmatively, the patent application will be classified as pending. So in this terminal node, there are all the patent applications that have sort of a moderate number of prior efforts, in other words, anywhere from 2 to 5 prior efforts, and which are relatively small in terms of their claim volume. In particular, they have claims less than 17. On the other hand, if the answer to this parent question, the claim volume, is it less than 17? If the answer to that question is not affirmative, then according to our tree, the patent application is classified as granted. Here, in that terminal node, there are all the patent applications that have a moderate number of prior efforts, again, anywhere from 2 to 5 prior efforts, but which are also moderate in terms of their size. The claim volume is anywhere between 17 and 23. Now, stepping back to the previous question where it was being asked whether the claim volume was less than 24, we already figured out what's going to happen if the answer to that question is affirmative. Now is the time to find out what happens if, in fact, the claim volume is 24 or higher. And it turns out that all those documents for which the claim volume is 24 or higher, and which have anywhere from 2 to 5 prior efforts, they are classified as pending according to our tree. And we have one more task to complete here. Again, if we step back to the previous question where it was being asked whether the prior efforts was fewer than 6, now that we covered actually the story corresponding to answering that question affirmatively, we have to find out what happens to these patent applications that have a substantial number of prior efforts. In other words, those applications that have 6 or more prior efforts, and actually they are classified as granted according to our tree. Notice all these labels pending or granted appearing on the terminal nodes again pertain to the status of the patent document 3 years after the submission. And so here's the story right in front of you, represented by this tree. And one final question that I want to discuss here is how are these labels appearing on the terminal nodes get determined? Like, for example, if you look at this label granted that appears on this very last terminal node that we just added. Why is it granted? How does the tree find out or determine that it should label the node as granted? So although on a tree you just see the corresponding label assigned to the terminal node, you can almost think of this label as some sort of a curtain behind which there are all the patent documents that end up in that terminal node. So in this case, in our case, for example, in this last terminal node, it happens that there are 21 patent documents that end up in this node, and out of them only 3 happen to be pending, and the remaining 18 are in fact granted. And since the majority of the patent documents are having granted status, that's why it's determined by the tree that the label that appears on the terminal node should be granted. Again, because the majority are being granted. And this is the majority voting, in a sense, process that appears within each node. And of course, the user may tweak the threshold and choose a threshold different than 50%, which is the threshold for majority voting, and choose a threshold such as 20%, 30%, 80%, or other thresholds, rather than the 50% that corresponds to majority voting. And so that's how the tree is being interpreted, and this is how the labels are being determined. Now that we know how to build and how to make sense of a classification tree, let's remember that at the beginning of the example, we separated 5 patent applications into a validation set, and now we have to get back to our objective and predict the status of each application from the validation set. How to do that? As you will see, it's the relatively straightforward part after we know how to make sense of the tree. For example, let's look at the first document from the validation set. It has no prior efforts, there are 2 inventors responsible for it, and it has 20 claims. We can think of almost like dropping this patent document at the root node and tracking it down along the tree to see which terminal node it ends in, and the label appearing on that terminal node pretty much will determine the class. And since this particular patent application has had no prior efforts, therefore the answer to the question appearing on the root node is affirmative, and therefore we'll move to the left branch, and thus we will end in this terminal node, and the label that will be assigned to this particular application will be pending. So this first application from the validation set is getting classified as pending. In fact, that's also the fate for the next 3 applications from the validation set, because each of them has less than 2 prior efforts. So they all will end in the same terminal node. And when we get to the 5th and last application from the validation set, we see that it has 5 prior efforts, and therefore we'll move to the right from the root node. We see, and for the same very reason, since it has 5 prior efforts, which is less than 6, we then will move to the left branch. And since the number of claims for that particular patent document is 22, then we will continue to the left and to the right to arrive at this granted status. And that's actually the class that this last and 5th patent application will get. So that's how simple it is to use the tree to predict the status of each patent application from the validation set. Now let us also not forget that for each application from the validation set, we actually know their true status, and that is what appears as the last column of the validation set table that you have on the left side of this slide. And so for the first patent document, we know the fact that it was pending 3 years after the submission. Second, third, and fourth were also pending 3 years after the submission, and the last one was granted. So it turns out that our classifications are very accurate, for this example, because for each application we were able to correctly classify, correctly predict the status 3 years after the submission. Now, so the first is correctly guessed, the second is correctly guessed, the third, fourth, and fifth, they're all correctly guessed based on the tree. How to summarize our predictive performance? One way to do that is by using the so-called confusion matrix. And as you can see, confusion matrix is a table which summarizes the predictive accuracy, in this case the classification accuracy, in a table. And we see that there were a total of 4 documents that were pending in our validation set, and all of them are correctly classified as pending. And that's the second element that you can see on the main diagonal, the number 4. And then if you look at the first row, you have only 1 document that in our validation set is granted, and we correctly classify that as granted, and that's the first element on the main diagonal. The sum of the elements on the main diagonal, 1 plus 4, divided by the total number of applications in the validation set, so 1 plus 4 over 5, and multiplied by 100, gives us the correct classification rate. So in our case, obviously the correct classification rate is 100%, since obviously we were able to correctly classify all of the applications. And 100 minus that will give you the so-called misclassification rate, which obviously in our case is 0. To conclude, also notice that there are a number of extensions to this rudimentary CART approach, including but not limited to things like bootstrap aggregation, random forests, and boosting. And we won't cover them here, but having understood the basic logic and the basic intuition behind the classification tree is going to help you to grasp these relatively more advanced methods later on. Also remember that classification and regression trees allow not only quantitative but also categorical independent variables, and that's also the case for regression. Also, although we just considered quantitative independent variables, we can very easily incorporate also categorical independent variables on the right hand side of the